Okay, hey, welcome back, class. Now we're starting some practice problems dealing with types of nuclear decay and learning just how to work these types of problems out. The biggest key to understanding and interpreting nuclear decay problems is to understand the different symbols and numbers that go with each type of decay. So let's go over each type of symbol before we even start into these practice problems. So first is alpha decay. Alpha decay is characterized by the presence of alpha particles, which is a 4,2 helium particle. So that's your key thing. If you see 4,2 helium, alpha decay immediately. And it occurs when there is an excess in the number of protons and neutrons in the nucleus. Then we have beta decay. Beta decay occurs in isotopes that are found above the band of stability. In order to make these nuclides stable, beta decay converts a proton into an electron and emits it. So this is how we get the beta signal shown as 0, -1 beta sign. So when you see that, you know it's beta decay. Don't get that mixed up with positron emission. Gamma decay doesn't necessarily show visible changes in the nuclear equation, but for accuracy's sake, we accompany it with other types of decay problems to show that there was energy or emission of gamma energy or gamma rays. Gamma decay is represented by 0, 0 gamma symbol. So the 0, 0 indicates there's not going to be any change in the formula. So the next one is positron emission, and it occurs in isotopes that are below the band of stability and is an attempt to increase the proton to neutron ratio. Positron emission converts a proton into a neutron. It is represented by a 0, +1 beta sign. Okay, so keep that in mind. That's easy to mix up with beta decay. But beta decay has a -1, positron emission has a +1. Finally, we have electron capture. This is another type of decay that occurs when the neutron to proton ratio is too small. Basically, during this type of decay, an inner orbital electron is captured and brought into the nucleus. It is then converted into a neutron, which is represented by the symbol 0, -1 e. Okay, so now we got all that out of the way, let's actually work some practice problems. For these first couple, we're going to say write the chemical equation for a single alpha decay for each of the following radioactive isotopes. Gold, 195, cadmium, 109, phosphorus, 32. Okay, so let's go back to gold, 195. So first of all, we see gold, the 195 is telling what's the atomic mass, so that's the top number. So you have gold, Au, 195. Now that bottom number is just the atomic number, which is 79. Okay, so we have for our first part, 195, 79 Au. And since it's going through an alpha decay, we're going to put our yield sign, which is our arrow. What I like to do first is put my particles and my numbers out. So in this case, we're putting our alpha particle out and fix the rest of the numbers. So I'm going to skip over a little bit of places, and I'm going to put my 4,2 helium, which is my alpha particle. Okay, and then now I got to figure out what my missing numbers are, and then my missing element from there. So remember, law of conservation of mass. Both things on both sides of the equations need to add up. So if we have 195 as our total mass on the left side of the equation, then we need that on the right. Well, we already have 4 with our alpha particle, so we need 191 more. So that top number is going to be 191. Well, then we need to account for our protons. So we have 79 on the left with our gold. We have 2 on the right with our alpha particle. So in order to make that up, we have to have 77, because 77 plus 2 is 79. Well, we got an element with 191 atomic mass and 77 protons. Now we just go look on the periodic table and find what element has 77 protons, and that would be iridium. So our alpha decay of gold 195 would be 195, 79 gold, yields 191, 77 iridium, plus an alpha particle. Okay, the next one, cadmium 109. So just like we did with gold, we put our 109 as the top part of our isotope for cadmium, and then we go find how many protons it has. If we look on the periodic table, cadmium has 48 protons. Now we go to our decay, so yield sign, then space out a little bit and write my alpha particle out for 2 helium. Okay, so now we can start writing our numbers for our mystery element. Well, we want mass to be conserved, so we have 109 on the left side, so we need 109 on the right side. Well, we have 4 with our alpha particle, so that means the other element must have 105 atomic mass units. We did the same thing with our protons. We have 48 on the left side. We have 2 on the right side, so we need 46 in our mystery element, because 46 plus 2 is our 48. Then we go look on the periodic table and say what element has 46 protons. That would be PD, or palladium. And then finally, for the last alpha particle one we have is phosphorus 32. So we put 32 phosphorus, or P, and its atomic number is 15, so that's at the bottom. Yield sign, then, like we've done on the other ones, we put our alpha particle out there, space a little bit and put our alpha particle out, and that's for 2 helium. Now we just need to figure out our numbers. So if we take our 32 and our phosphorus, in order to get to 32 on our right side, we need to add 28 to the 4 that we already have. So the atomic mass of our mystery element is going to be 28. Then we do the same thing with the protons. We had 15 with phosphorus. On the right side, we have 2, but we need to account for the rest of the 15, so we need 13 more. So we're going to have our element has 28, 13. Well, the element that has 13 protons is aluminum, so it'd be 28, 13 aluminum. And that will give us our equation of 32, 15 phosphorus yields 28, 13 aluminum plus an alpha particle. Now we can move on to our next set. Write the chemical equation for a single beta decay for each of the following radioactive isotopes: copper 66, bismuth 210, tungsten 188. Okay, so for our beta decays, let's start off with copper 66. Okay, so we go copper 66. We know it has 29 protons because that's its atomic number on the periodic table. So just like we did with our alpha particles, we're going to say yield and then space it out a bit and write our beta particle out this time, which is a 0, -1 beta sign. Okay, so this is going to be a little bit different. We want mass to be conserved, but we have a negative sign with our beta. So that means we're going to have more protons in our element to account for that negative sign. So first of all, let's get the easy part out of the way. That 0 on the top makes it where we have to have 66 atomic mass units for our mystery element. Now we got to figure out our protons. This is where it gets a little tricky. So we have 29 on the left side. We have -1 on the right side. We have to add 30 to it to get so that we have 29 on both sides, because 30 minus 1 is 29. Okay, so we have an element with 66 and 30. That would be zinc, because zinc has 30 protons. So that would give us a beta decay of copper 66 would be 66, 29 Cu, yields 66, 30 zinc, plus 0, -1 beta sign, or beta particle. Next one, 210 bismuth. So 210 bismuth's atomic mass is 210 on this one, but its also atomic number is 83. So we put 210, 83 Bi, yields, space it out a little bit, put our beta sign in there, or our beta particle, which is 0, -1. Okay, so that doesn't affect the atomic mass, so we can go ahead for our missing atomic mass. We're going to say that's 210. Now we have 83 protons on the left side of the equation and a -1 on the right side. So we're going to have 84 protons to have mass conserved. Okay, so if it's 84 protons, we look on the periodic table, that's PO, or polonium. Okay, so that would give us a beta decay of 210 bismuth decomposes into 21084 polonium plus 0, -1 beta sign or beta particle. Okay, final one in our beta particles, tungsten 188. Okay, we know tungsten, if we look in the periodic table, it has 74 protons. So we have 188, 74, and W for tungsten's atomic symbol. That's going to decompose. Let's space out, put our yield sign, space out, and then put our beta particle. And so now we got to account for the rest. Well, our beta particle is 0, -1, so again, does not affect the atomic mass. So whatever element we have has 188 atomic mass units. But we got to figure out the number of protons. That's going to be what changes. So we have -1, and we're wanting to get to 74. That means we're going to have to add 75 to it. So our mystery particle is going to be 188, 75, and the element that has 75 protons is Re, or rhenium. So that would give us a beta decay of 188, 74W, or tungsten, yields 188, 75 rhenium plus a beta particle. Now we can move on to positron emission. So write a chemical equation for a single positron emission for the following radioactive isotopes: carbon 11, nitrogen 13, fluorine 18. Carbon 11 to start out. So that would be 11, 6 carbon, because carbon's atomic number is 6. Okay, so we're going to space out a bit. Like we've done our yield sign, we space out a bit, and we write down our particle first. Okay, well, a positron emission just has 0 + 1 beta sign. Okay, so we have those two. Now we got to figure out our mass and our missing element. So the 0 indicates that mass is not going to change. So, okay, so whatever element we have has atomic mass of 11. That's going to be the top number. Well, we have 6 on the left side. We have +1 on the right side. We need to have them equal out. So that means we need 5 for our missing number of protons, because 5 + 1 is 6. So our missing element is 11, 5 boron. So our positron emission gives us 11, 6 carbon emitting 11, 5 boron plus a positron. Nitrogen 13. Okay, nitrogen's atomic mass is 7, so it's 13, 7 in. And we're going to put our yield sign, get our positron symbol out, so 0 + 1 beta sign. And now we got to finish our missing elements, or missing numbers. We have 13 as your atomic mass for nitrogen, and we have 0 with our positron. That means our element must come up with 13 atomic mass units. Now we go down to our protons. You have 7 with the nitrogen. We have +1 with our positron. So that means it must be 6. So 13, 6 carbon, or carbon 13. So 13, 7 nitrogen will decompose into 13, 6 carbon plus a positron. Okay, our last positron one. Then we take fluorine 18. Well, the atomic mass is 18, and fluorine's atomic number is 9, so that's 9 protons. We put our yield sign, space it out a bit, put our positron, or 0 + 1 beta sign. Okay, now we can just do our math for our missing parts. Well, whatever it is, it's going to have 18 atomic mass units because it's all going to come from that element. And we're trying to get to 9 protons. We have 1. So whatever element it is, it has 8 protons. So it's going to be 18, 8. Well, the element that has 8 protons is oxygen. So 18, 8 oxygen. Now if we just put it all together, we have 18, 9 fluorine decomposes into 18, 8 oxygen and a positron. And then we get into electron capture. So we need to write a chemical equation for a single electron capture for each of the following isotopes: aluminum 26, nickel 59, potassium 40. Okay, our last set for this type of question dealing with electron capture this time. Okay, so we're going to take aluminum 26. Aluminum has 13 protons, so its atomic number is 13. So if we want to do electron capture on it, we're going to have to add our electron to it. So this is going to be different. Instead of having the yield sign next, do our plus sign and have our electron present. So our electron is 0, -1e. So far our equation should read 26, 13 aluminum plus 0, -1e. Okay, so we have to have mass conserved and everything conserved. Well, the 26 with your aluminum and 0 with your E, that must mean we have 26 atomic mass units on the right side of the equation as much as it must match the left side. So if we need them to both match up, we have 13 to start out with. We subtracted 1 from it because the -1 with the electron. That's going to give us 12. So that must mean we have 12 protons on both sides of the equation. So we have 26, 12 is our numbers. Well, the element that has 12 protons is magnesium, so it's 26, 12 magnesium. So if we read the full equation out, it should be 26, 13 aluminum plus 0, -1 electron yields 26, 12 magnesium. Okay, so here comes another one, nickel 59. So nickel's atomic number is 28. And we take nickel 59, so 59, 28 nickel, plus our electron, 0, -1e. And that's going to yield, if we do our math, you should have 59 atomic mass units as the top one, and then 28 minus 1 is 27. So that's going to be cobalt. So 59, 27 cobalt. So the equation should read 59, 28 nickel plus 0, -1e. That's going to give us 59, 27 cobalt. Our final electron capture one will be potassium 40. So potassium has 19 protons, so it's 40, 19K. And then we're going to add our electron to it, so 0, -1e. And that's going to give us, if we do our numbers right, it's going to be 40 and 18 as our numbers. Well, the element that has 18 protons is argon, Ar. So it should be 40, 18 argon, giving us a total of 40, 19 potassium plus 1 electron gives me 40, 18 argon. So I hope these helped you out. They'll be able to help you through any worksheets that you may be having. I gave you several different ways to look at these problems and worked out several different types of nuclear decay, so it should give you a good amount of examples to work through. Keep up the good work, and I'll see you next time.